All right, anybody have a question in the sample 3 in those first 16 problems that they would like to take a look at? 16. Okay, yeah, this was an interesting one here. I did visit with a few people about this one. This is one of those. It says if this is a positive integer, then what is this limit? You really don't have to do a limit. This is a no calculator one. What you want to do whenever you see one like this is that sigma integral conversion that we did. The sigma integral conversion. All right, now, so forget the limit as n goes to infinity. That just means what? When we did their sigma to integral conversion, what did that mean? What did that mean? Oh, come back. Okay, forget that part for a second. Let's just talk about this part. Okay, what was the 1 over n? The dx, the width part, right? So we had our, if we were going to write our sigma, so what we want to do is write it as a sigma, then write it as an integral, and then just do the integral. Then just do the integral, and that's how we would find the answer. So the 1 over n is like the delta x. It's out here. So that's my width. So if I make myself a little x-axis here. Now I notice each one of these functions has a sign, and it's got 1 pi, 2 pi, 3 pi. So what's that going to be in here? That's the I pi, and then over n, and then we've got I equals 1 to n, right? Because the last one has n pi over n. Now normally what we did with these is we said, okay, this part, the 1 over n, that's going to be the dx, right? And this part on the inside is the what? This messy stuff on the inside is what? That's the x. So what many of you were thinking is that then this would be that, like so. But it's not. Why not? There's more to it there. What's in here that is not normal? Or is not, I mean, if I was to expand this, like I'd plug a 1 in for I and a 2 in for I. The pi. Here's why. Because normally, remember, when I don't know if this starts at 0 quite yet or not, but if my width is 1 over n, then that means, let's say we start at 0. Then the next width over would be 1 over n, and then the next one would be 2 over n, right? The next one would be 3 over n, if that's my width, right? And that is my width. We know, because it's setting right out here. 1 over n, 2 over n, 3 over n. When we do our rectangles, that's what we plug in for the x, right? Is that what's getting plugged in here? 1 over n, 2 over n, 3 over n? No, it's pi over n. 2 pi over n, 3 pi over n. So there's this extra pi setting around there. So this pi right here is actually in this function, the 1 over n, because see, normally what we would have had is a pi over n out here, and that would have been our width, pi over n. And then we'd have had 1 pi over n, 2 pi over n, 3 pi over n. Pi over n would have been our width, and there would have been a match, and then this would have been the x, and then the pi over n would have been the delta x, or the dx. You see what I'm saying? But because the width is 1 over n, it has to go, the x's have to go 1 over n, 2 over n, 3 over n, 4 over n. So this part, the I over n, is the messy part that's the x. The pi is still in there. So this function actually is that. Now we could have done some of those, but I wanted to keep it a little simpler when we were doing it. So we made sure that all of our different sigmas we had, where the messy stuff in here, that's where the x was. But now you've got to understand that it could be a situation where you've got this width, there might be an extra thing in there, okay? And that's what is going on with that. So the function is actually sine pi x, because you have to get a match between your width and the numbers that you plug in. Because remember, these are like right rectangles, right? Because it starts at 1 here. So your first right rectangle would be that, and your next right rectangle would be that, and your next one would be that. These numbers here are what get plugged in for the x. So we have to look at this and think, well, 1 over n, we plug in for the x, but what do we get when we plug a 1 over n in? We get pi over n. Oh, there had to have been a pi setting there when we plug the 1 over n for the x. So that's how you would know that. Now, where does this start? Well, it has to start then at 0. So, because if we go 1 over n, 2 over n, 3 over n, all the way to n over n, what have we plugged in? What's the last thing we plug in? A 1. So we're going from 0 to 1, and then you have this. See, some people thought we're going from 0 to pi maybe here because you got your last thing you plug in is a pi. Well, no, that's because the pi is right there. The last thing we plug in for x is a 1. And then we get that pi. So the integral is actually 0 to 1. So that was kind of a tricky. So you do the antiderivative of sine, and that is negative cosine. So that'd be negative cosine pi over x, or pi x, and we have to kick out a 1 over pi, right? We have to kick out the reciprocal of that in there. And then we're going to go from 0 to 1. So we plug a 1 in, we get cosine pi, that'd be negative 1, times negative 1 over pi, so that'd be 1 over pi, and then minus, and then we plug a 0 in, cosine of 0 is 1. 1 times that would be negative 1 over pi, so that turns into plus, so 1 over pi plus 1 over pi would be 2 over pi, and that's where that comes from. Okay, so that's that integral to sigma stuff we were doing. We got to take that, make it a sigma, turn it into an integral. A lot of the ones we've done in our packets have been a little simpler than that. They went more easily. That one was a little tricky. Okay, but hopefully if we see that again, we'll handle it. Okay? Any others? Any others? Okay, later in the week we'll do a little more work in this packet. Thursday for sure you'll have some work time there. Maybe on Wednesday a little bit. We'll see how much the new stuff we get. Well, actually tomorrow maybe a little bit. Tomorrow we'll be caught in between going on to the new stuff. I mean, I don't know. We might do some of that. Then if we do that, then we got kind of a gap between the quiz. We could do the quiz early. I hate to do the quiz on the day I'm not here. So I'm not quite sure. Right now the plan is still to do the quiz on Friday. All right. Well, if there aren't any others, let's talk about this new thing we have to do today, which is in section 6.2. So we go back and we think about all the stuff we've been talking about with over and under approximation. I don't think, for the most part, many of you found any of this too terribly difficult, what we've been doing about when left and right are over and under approximations, when midpoint trapezoids are over, depends on concavity. You know, when we've been writing kind of the new way we've had of writing these out, left, right, midpoint trapezoids, we've got Simpson's rule now. We've got these formulas, you know, for trapezoid and Simpson's rule. You know, we've got our rule that if we have a single digit approximation we have to do, we write it out by hand. If it's double or more, we're going to use that area program in our calculators. Okay, speaking of the calculator, let's go ahead and see if we can get logged in here. See if that'll work for you. Is that working? Looks like we're getting logged in. Okay, good. All right, so section 6.2 is about error-bound formulas. Or actually, we might call, another way of thinking of them is max error formulas. Max error formulas. Okay, so we've been prepping for figuring out how the calculator knows. You know, when it gives you an answer to an integral, and the one we're going to work on today is we're going to work on this one right here. the integral from 0 to 1 sine of x squared dx. Okay? And so 0 to 1 sine of x squared. So this is one we cannot do an antiderivative on. Okay? And so we cannot find the exact answer. So if we go, let's find that. Oh. Who's not logged in? Doug, are you logged in? Why not? It'd be hard to log in. Come on in. Who's this? Noah. No. All right. So, we don't need to do anything. Just well, go ahead and do that integral. Go ahead and type that integral in. 0 to 1. Sine of x squared. And notice it remember, we talked about how it tries to give you an exact answer, but in this case, it will go ahead and hit enter. And it gives you a decimal. And we've got set on float, so we should get 12 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think that's the most it'll give you. And the calculator is guaranteeing, basically the calculator is saying that we know that this is accurate out to 12 decimal places. This is accurate out to 12 decimal places for the exact answer. How in the world does it know that? Because if you can't find it by an antiderivative, is it just guessing? Is it just doing like a million rectangles so it feels pretty confident that it's that accurate? Or is it doing a million traps? You know, what's it doing? And we did it fast. You know, how's it doing that approximation and knowing that it's accurate out to 12? That's what we're going to investigate today. Okay, so what I'm going to do, if you want to look on page 387 in your book, 387, what we're going to do today is we're going to develop these formulas. Now, how much of this you write out, I don't care. This is one of those things where I'm going to show you where the formulas come from, but at the end of the day, all you really need to do is be able to use the formulas. Okay, but I think it's valuable to go through where these come from. So 387, you see these formulas at the top of the page. Now your book calls them Theorem 3 error-bound formulas or whatever. So anytime in your homework today, when they talk about use the Theorem 3 error-bounds, this is what they're talking about. You're not going to have to memorize these. On the quiz, I will give you these formulas. You're going to have to know what the parts of the formulas are and how to plug in the parts of the formulas. But I will give you the formulas. You won't have to memorize. All right. So the first thing let's first talk about left and right rectangle. So what causes a left and a right rectangle to be over or under? Increasing or decreasing. And what causes the amount that it's over or under? How steep it is. And what measures steepness? Slope. And how do we have a finding slope? On a curve function? Derivative, right? The derivative of the function measures the steepness. Now, the problem is the slope is changing, right? The slope is changing on a curve all the time. So the amount of error that a left or a right rectangle is going to have is going to be determined by the derivative of the function. So that is the first key thought, and we've already talked about that, okay? But that's the first key thought in doing this. So here I have a picture. And again, how much of this right now is totally up to you. So here I have my blue function. Now it's pretty flat, so there's not a lot of air, okay, in this left rectangle right here. But what this line here represents is the steepest, because here's what we want to do. The whole gist of what we're doing today is this. Figure out what causes the error, which we just said is the derivative, the slope. And figure out over that interval when it's the worst. Let's do a worst case scenario. In other words, let's find when this graph is its steepest, right? Well, what would that be? The steepest. If f prime is the steepness over that interval, where would be the steepest? That would be the max of f prime, right? So our worst case scenario is where f prime has a max. Now, we could go through and do the whole business of how would you find it? We'll do its derivative, which would be the second derivative, set it equal to 0, right? It's going to happen at an inflection point, isn't it? Isn't that usually where the slope's the steepest? Unless we get into like a sharp point graph, and we're not going to mess with all that. Well, I'm not going to make you do all that. We're not going to do the derivative, set equal to 0, find the max. We've done tons of that kind of stuff, right? You'll have plenty of problems where you have to do that. But this problem would be too long if we had to go through that. So we're going to let the technology do that for us. But this is what K1 is going to be. So you might want to jot that down. Because if you look on page 387 in those formulas, the top two formulas there, you notice they have this thing called K1 in the formula. All right? Well, K1 is going to be the steepest, the max value of f prime. Now, it could be positive or negative, and we don't really care about that, do we? I mean, if you had a graph that went up and it went down, like this one kind of does. It goes up, then comes down, then goes up. Where's its steepest? Let's say it has a slope of 2 at one point, and then later it has a slope of -3. Which one of those is the steepest? The -3, right? That's what we care about. We don't really care about the negative positive business. That just means it's up or down, means it's an over or under approximation. So I don't really care about that part. So we're going to actually say the K1 is the max of the absolute value of f prime. All we care about is where is f prime have its biggest number. And we don't care about it being negative. So if the f prime goes up to 2 and then later goes down to -3, we want to use 3 as our K1 value. Does that make sense? Because that's the steepness of the line. We don't care if it's steep going up or steep going down. Either one of those is going to cause our left rectangle to be off. Now, this is just one left rectangle, right? We're just doing this in one subdivision to keep things simple. All right? Now, so what we could do is we could take this one subdivision, we could look at our f prime, and we could find the max of f prime in that interval. And then what this line represents here is what if that curve, what if the blue curve kept that slope the whole time? Well, how much would it be off? Well, it would be off by that much, wouldn't it? My left rectangle, that is. Does that make sense? And this would be same for right. If this was a right rectangle, right, we would go up here, and then how much would it be off? Again, it would be that same thing. It would be this whole triangle. You see what we're doing? What we're trying to do is figure out the worst case scenario. Now, the actual error is right in here somewhere, right? I mean, this is the amount that it's off, the gray. That's how much the left rectangle is off. But the worst case scenario is what if this blue graph, let's find where it's the steepest, and let's pretend that it had that steepness the whole time. You see what I mean? We know it will never go steeper than that, right? How do we know it will never go steeper than this? Because we found the max slope, right? What we're doing here is saying we found the max slope, so let's pretend it has that slope the whole time. We know it'll never go steeper than that, so we know the error will never be more than whatever this triangle is. So let's figure out what this triangle is. So the amount of error in this one triangle, and this part I don't care if you really write down right now, would be 1/2 the base, well, what's the base here? That's one width, right? That'd be delta x. Now, what's our formula for delta x? B minus A over N, right? And then, so it's 1/2 this base, and then what's this height? Now, this is going to be a little hard. Let's see, we got slope. Hey, you know what? Let's call this the rise, and let's call this the run, right? And the slope is the rise over run. Now remember, K1 is the slope, right? So the K1 would equal the rise over the run. So, but what I need here is what? I need the rise right here in my formula, right? What I'm trying to do is the area of this triangle. So it's 1/2 the run, which we know is a delta x, times the rise, right? 1/2 base times height. So what's the rise? Well, the rise is K1 times the run, but what's the run? Delta x, which is B minus A over A, right? So the rise is K1 times, it's like slope times run, which gives us rise. So in place of rise here, I'll put K1 times B minus A over A. So put that all together, and I get 1/2, I get B minus A over N quantity squared, and then I get times K1. But now that's the amount of error in only one subdivision. How many subdivisions are there? I mean, it'd really be a pain to do this in every subdivision, to go through and find the max F prime in every subdivision. That would be more accurate. But what we're going to do instead is we're going to find the max F prime over the whole interval, A to B, and pretend it has that the whole time, right? That's what we're actually going to do. Okay, so let's pretend that K1 is the max slope, not just in this subinterval, but it's the max slope over the whole A to B. So this is just for one subinterval. This is how much error there's going to be. So how much error, what's the max error for the whole interval? We have to times this by how many subintervals, which is n, right? So this is the error in one subinterval, and then we have to multiply that by n. So let's rearrange this a little bit. Let's square the top and the bottom of this. So I'd have, so what am I going to have on top? I'd have K1 on top. I'd have B minus A squared on top. I'd have an N on top. What would I have on the bottom? A 2 N squared. And then won't this N cancel one of those? And voila, look at page 387. Isn't that the formula in the top there in that box on page 387? For L, and it would be the same for R. Okay? So now remember what that is. That's the max error. That's the worst case scenario. And it's the worst case scenario because we've taken K1 and let it be the max of the absolute value of F prime. We've let that be the steepest that the graph ever is. And then what we've done is assume that the graph keeps that steepness the whole time. And if it does, then this would be the error. Well, we know it probably doesn't have that much error. If it had that slope the whole time, it'd just be a line. So we know it probably doesn't have that much error, but we know it can't have more error than that. And that is how the calculator knows. And we'll get into calculating that here in a second. All right. So if you go to, so if you want to write something in your notes then, I guess we could put down this formula over here, okay? And then maybe I'll do, well, I've just written it once because this could be L sub n and R sub n. Now remember the left side of this, is the amount of error. And we'll get to the right side over here in a little bit, okay? But the left side of this is the amount of error. So I is the exact error area. L or R is our approximation. So when you subtract those, that's how much error. And what we're saying is the amount of error is less than or equal to this. So that's why this side is our max error. Because we're saying the amount of error is less than or equal to this. Now remember that K1 is the max of F prime. Okay, now we'll show how we're going to, in a minute, we'll show how we're going to do some formula, do some example problems. on there. Okay? All right. Now what about midpoint and trapezoid? So now we've got these formulas for midpoint and trapezoid. Okay, now this is a little trickier to do. But again, you're not going to have to do it. You're just going to have to be able to use the formulas. But I do like to show this. I think it's worthwhile. Okay, so here's what we're going to do with midpoint and trapezoid. Now, what determines midpoint and trapezoid? Concavity. And what measures concavity? The second derivative, right? So what are we going to do? The same scenario. We're going to pretend that our function, whatever the steepness, we're going to call this K2 now. K2 is going to be the max of F double prime. Now remember we said this last week, if you have a graph that has a second derivative of 2 and one that has a second derivative of 3, the one that has a second derivative of 3 is more curvy, more concave, and so therefore it has more error. The midpoint and the trapezoid are going to have more error. So we're going to call K2 the max of F double prime. So we're going to do the same thing. We're going to pretend our function. We're going to figure out the max of F double prime. And we're going to let our calculators do it for us. We're going to figure out the max of F double prime, and we're going to pretend that the function has that second derivative the whole time. That's going to be our worst case scenario. Okay? Now, the problem is, before, when we did this, to show a function that had this slope the whole time, all we had to do was draw a line with that slope. Well, how do you draw a function that has a certain concavity? It's still going to curve. So we can't do it with a picture. So what we have to do is we have to do it with a formula. So again, I wouldn't necessarily have you write all this down. So what we're going to do is assume that our function has F double prime of K2 all the time. So we're going to assume that our function is where F double prime is K2. So what would F prime be? Well, let's do the antiderivative of that. Remember, K2 is just a constant. So what's the antiderivative of K2? K2 times X. We could put on a plus C, but that's just going to shift it around. We don't care about that. So we'll just let C be 0. And then what would F be? One half, or K2 over 2, so 1/2 K2 X squared. Okay, this would be a function that would have K2 as its second derivative all the time. Now remember, K2 is the worst case scenario. K2 is the max F double prime we could have. So what I've done is created a function that has that as its second derivative all the time. Now what I want to do is find out how much area is under that. Okay? Now, what that would be, so what I'm trying to do is this. Okay, so what I did here is I just found this area right away, and that was my formula. But what I could have done is what I could have done is I could have found the area under my made-up function. This line right here is my made-up function, right? My worst-case scenario function right here. I could have found the area under my made-up function, right? And then I could have subtracted my rectangle. Does that make sense? And then that would have left me this, right? So I could have done the area under my made-up function minus my rectangle approximation, and then I would have gotten the formula too. I could have done that. All right. Well, that's what I'm going to do on this one. I'm going to do the area under my made-up function. So I'm going to do the area from A to B of 1/2. Oh, no. I'm sorry. I'm not going to go from A to B. I'm going to do like I did this one. We only did one subinterval. Remember that? So I'm going to do, so on this one, to make it easier, I'm just going to do one subinterval. Now, to make it really easy on myself, I'm going to call my subinterval, I'm just going to call it Z, I'm going to let H be my width. Right? I'm going to let, just to make it easy on myself, I'm going to let H be my width. Okay? All right, so I'm going to do the integral from 0 to 8. So I'm just going to do one subinterval. This will just make it easier. And we'll sub the H out of there later, as H is the width. Okay? So I'm just going to do one subinterval. So I'm going to do this actual area under that. Okay, that's not bad. I can just raise that up, divide by 3, so I get 1/6 K2 x cubed from 0 to h. I'm going to plug an h in there. So I get 1/6 K2 x, or that'd be h cubed. And then I plug in a 0. That's just going to be 0. Okay, so there it is. Okay, so that's it. So that's my area. Like when I was doing this one earlier, that would be all this area. Okay, now I have to subtract off. Now I have to subtract off my midpoint, and I have to do it separately for trapezoid because they're not the same like they were with rectangle. Okay, so let me do a midpoint. Let me do one midpoint rectangle. Okay, so let's say I had a midpoint rectangle. Let's do that in blue. Okay, so let's say I had a midpoint rectangle right here. Well, what would that area be? Well, it'd be one width, which is h, right, times this height. What would that height be? Well, what would this number be that I'd be plugging in? 1/2 h, right? And I'd have to plug that into my function, and this is my function right here, right? So let's plug a 1/2 h into here. So what would I have? I'd have 1/2 K2, and then let's plug a 1/2 h into there. See what I'm doing? I'm just trying to find out what my midpoint is. And then I'm going to subtract those two, right? The area under my worst case graph minus my midpoint, that would be my error. That'd be the amount of error. Okay? So let's simplify this. This would be 1/4 times a half. That would be 1/8. What would I have? H cubed and then a K2. Okay, so that would be that. All right, with me? So that's midpoint. Now let's do a trapezoid. Let's do a quick trapezoid. Trapezoid is 1/2. So let's say I had a trapezoid here. So let's go black to black. Let's say that's my trapezoid right there. Okay, so it'd be 1/2. What's the height of my trapezoid? That'd be h. And then I need these two heights. So the first one would be a 0 plugged into my function. What do I get if I have a 0 plugged in here? There's 0. Okay, and then what do I plug in? For this one, I plug an h in, so that'd be 1/2 K2 h squared, right? I just plug an h in. So that'd be my one trapezoid. So let's simplify that a little bit, and so that'd be 1/4 K2 h cubed. With me? Okay, so that's one trapezoid. This is one midpoint, and this is the area under my worst case scenario, kind of like this area here. So now what I do is I do this area minus my trapezoid or minus my midpoint, and that'll give me my max error. That's what I'm doing. Okay? All right. Thank God you're not going to have to do this, right? All right, so it's not bad. So now all I need to do is subtract these. So 1/6 K2 h cubed minus 1/8 K2. Oh, look at that. They're like terms. They're like terms, aren't they? K2 h cubed. So all I have to do is do a common denominator. So what would I have? 24 here? So that'd be 4/24 minus 3/24. So it's simply 1/24 K2. And then what did we say h was again? One width. So isn't h just b minus a over n cubed? And then we said that's only one subinterval, so we times that by n. All right? And so that would be that one. And then this one would be 1/4 minus 1/6, right? Or the other way around. I don't care if I get a negative here, right? Negative or positive, doesn't matter. So 1/4 minus 1/6, that'd be 12 as a common denominator. So that'd be 3/12 minus 2/12 would be 1/12. So the trapezoid would be 1/12 K2 h cubed. H is b minus a over n cubed. And then times n. Does that make sense? And notice, look at the max errors. Compare midpoint to trapezoid. What's different? The midpoint has a 24 down here. Trapezoid has a 12. What's that mean? That's the max error. The midpoint has how much error compared to the trapezoid? Half as much. Half as much, which we've been kind of saying, right? The max error is going to be half. Now, the actual error is roughly half, but the max is going to be half. So otherwise, they're the same formula. So what's going to happen? This will be cubed. So the b minus a will be cubed. The n cubed will cancel with that n, so you have an n squared on the bottom. But you have b minus a cubed, you have the k2. If we go back a page, sure enough, that is exactly what these two formulas are. K2, b minus a cubed over that. The trapezoid has a 12 there instead of a 24. So I didn't want these to be totally mysterious. They might now just be semi-mysterious. Okay, but so what we have is we're saying that the actual answer minus our midpoint approximation, which means that's the amount of error, has to be less than or equal to this number. This number over here is the max error. That's the most it can be off. And it's dependent on the second derivative. K2 is the max of f double prime. All right, that's where they come from. Now, what's it going to look like for your homework? This is the part you want to pay attention right down. So we're going to take this integral right here, our 0 to 1 sine of x squared dx, and we are going to see our max error for an L10, an R10, an M10, and a T10. Now, since those are double digits, you're allowed to go to your calculator to do those right now, right? So let's go on to your calculator. Now, we do know the exact answer to this. Let me call this I, because that's what they do in your homework. And we know from what we wrote earlier, or what Noah did for us earlier, we know he got an exact answer of that. So 0.1, 0.310. What was that? 310. Go back. 2683. So we know the exact answer, at least according to our calculator, is this much. So everybody go to your area programs now. Let's make sure we all remember how to do this, because you might need to do it on the quiz at some point. So we go into our documents. Right? It was in the My Library, My Lib, called Area. Okay? To run it, you might just have to hit enter, probably. Right? It was RAM parenthesis is what you could type in and hit enter, but that's all you do on that page. And so if you just hit enter every time, it runs the program. I would do like 5 decimals generally. I think you want 3, but then you got to put your function in. And what are we doing? 0 to 1, I think we were doing. And we're doing 10 subintervals. Okay, read me the, Noah, read me the left.
0.269.
And the right.
0.353.
Okay, the midpoint.
0.30962.
And the trapezoid.
0.3111731.
Okay. Now, our lefts are under, our rights are over, our midpoints are under, our trapezoids are over, right? But now what we want to do, and the homework questions will be worded kind of like this. Something like this. What do the error-bound theorems predict for these approximations? Or find the error-bound. And it could pick just one of these maybe, right? Or all of them or whatever. Find the error bounds. Find the max error, right? Use the formula, find the max error. These would all be ways of asking kind of the same question, saying you're going to use this formula, this Theorem 3 formula. So here's what it would look like. Let's focus on left and right first because they're the same. So let's write down I minus L10, right, is less than or equal to, and now on this side we're going to fill in our formula. Now, I'm going to put a box for the K1, right? That's where K1 is going to go. I'm going to put a box there. As a matter of fact, on your homework, or on your quiz, and your homework, it's going to be very important for you to do this because on the quiz, I'm going to be looking at what you put in that box. That's a big part of your credit for the problem is what number you put right there. Okay? And then here we have b minus a, so that'd be 1 minus 0. And was that squared then in that formula? Okay, I can't remember. Here it is right here. Yeah, it was squared. Okay. All right. And then on the bottom would be what? 2 times 10, which, yeah, you could just write 20. That'd be fine. All right? So it's really easy. The only thing we need for the formula, the rest of it's all given to us. N is the number of subintervals. The b minus a is the numbers here. What we have to do is find the K1. Okay, so what was K1? K1 is the max of the absolute value of f prime, right? So the easiest way to do this is to go to our calculators, and we're going to graph f prime. So now, if I were doing it, I'd probably let the calculator do the derivative. It's a pretty easy derivative, so I might go onto the calculator screen right now and do the derivative. But I think a graph of f prime is what you want. So I would have the calculator right now, yeah, do the derivative, even though it's a pretty easy one, and you know, you can probably do it just fine yourself, but sine of x squared. But this way you get to do a lot of copy and paste. Okay, that's the derivative. We want the max of that. Now, absolute value, how are we going to handle that? You've got two choices. You can either just graph the f prime and then look at both the positive and the negative part of it. Remember when I did the example, I said f prime of 2, and then if it's down here at -3, you want to use what as your K1? You'd want, not -3 though, you'd use 3, right? Because K1, K2 are always positive. So that's one way to do it, is just graph f prime and then look at that. Or probably the smart thing to do is graph the absolute value of f prime. And then you can just look at its highest point. That's probably the smart thing. So let's do that. So let's go back to your graph screen now. And so let's go ahead and put in absolute value. Now probably the easiest, just type ABS. You got to be careful. You can't use the vertical bar that we use over here. You can't use that for absolute value. Where is absolute value, by the way? Is it under the trig? No?
It's with the derivative.
Oh, it's with the derivative, right. If you go in here, yeah, you can go and grab that if you want. Or you can just type ABS parentheses. You could do that too. Now, I would copy and paste. So, you could type it in right now if you want. Or from your calculator screen, we could have done a copy and paste. Yeah, see, you can arrow up here onto that. Now that it's highlighted, you can just hit Control-C for copy. Control-C, and then go back to your graph screen, and then put your absolute value back in there. And then hit Control-V for paste, just like you would on a computer. Yeah, copy and paste pretty slick with this. Okay? So you can copy and paste. Now, because here's the danger. If you just type this, remember, if you type X cosine, that's a problem, right? Because it thinks that's just one word, XCOS. You'd have to make sure you put a time sign in there when you copy and paste, takes care of that for you. Okay, now go ahead and hit Enter. Now, let's do a couple of other things. We get a really crazy graph, but we only care about this graph from where to where? 0 to 1. So I'm going to show you a couple little tricks here. That way, I've shown you this before, but it really works slick here. So we're going to go into our window, and we're going to go window settings, yeah, and we're going to set our X from 0 to 1. And I'm not going to mess with the Y right now. Hit OK. Now I could trace right now because I can see my max, but sometimes you can't see your max. So go ahead and go to your menu to zoom. Does anybody remember the zoom we use here? It's called Zoom Fit. Zoom Fit. And what Zoom Fit does is it'll take your X window from 0 to 1 and it'll fit the Y's in there appropriately. Now we can simply trace and use that little cheat we have with the maximum. So remember, this is f prime that we're graphing here. We just graphed the absolute value of f prime. And this is what you will have to do on these questions on the quiz, where you're using these formulas. And there'll be several of them probably on the quiz. You graph f prime. We're going to do f double prime here in a minute. Absolute value, we want to find the max, because remember, what this number we're about to find is the steepest that this f graph would ever be. And did it say maximum? There you go, it says maximum right there. Now, how many digits do we need? Well, I say we're doing it on the graph. Let's take all 5 of those for right now. And then we'll talk about how many we might need. 1.28367. Whoops, I'm going to write that over here. 1.28367. Is that what it was? All right, now, let's talk about this before I put it over here into my formula. There's another number after this 7. We don't know what it is, right? But there's another number out here, right? We assume that that's round. Could be 7.1, 7.2, might have been 6.8, right? I don't know. Now this is kind of a technicality, but I'm going to make you do it because I want you to understand what K1 is. K1 is the worst case scenario. Chances are that F graph does not have this as its slope the whole time, right? Pretty sure of that. We know, we just saw the F prime. But in this formula, this is supposed to represent a number that is the steepest the slope could ever be. If I put 1.28367 in here, technically, is that correct? Is that number the biggest that could ever be? Couldn't there be a 2 after this? Couldn't this be 1.28367 So would 1.28367 really be the biggest the slope ever is? No. Now I know that's a technicality and it's okay, but I think it's important to the underlying concept here. So if you wanted to use this many decimals, I think you ought to round up that last number, always. And then you would be guaranteed that that would be true. Now, I'm not sure we need to go this far, right? So what I'm going to say is let's go 1.284, just for our example today. Let's go 1.284 as the number we're going to use for K1. If on the quiz you did 1.283, I would dock you points because you did not catch this concept that this number we're finding here is a number that the slope will never go above. So some people might get smart out and say, well, I'll pick 4 then. Wouldn't 4 be a number that the slope's never greater than? Or 5 or 100, right? Those would all be numbers that the slope would never be bigger than. Problem is, those would give us a less useful max error. Okay? So what we want in our formula is the most useful number we can get. That is still a guarantee that the slope will never go higher than that. Make sense? And so it kind of depends on how big this number is. Right? If this number was 99.283, is there really much difference between 99.283 and 99.284? Or even between 99.3? You know what I mean? I can almost just go here and round that then. Now, when you got a number this small, like 1 point something, then there is a bigger difference between 1.2 and 1.3. Does that make sense? There's a bigger difference between 1.2 and 1.3 than there is 99.2 and 99.3, right? So the value of this number, where you round it to and how far you go is kind of dependent on how big it is. And so that's something I think we want to take into account. You'll see as we do some examples here. All right, now just get on your calculators and let's just type this in. Okay, so let's go to the calculator page, and let's go 1.284 times, what was it? 1 divided by 20. All right. And there we go, 0.0642. Now, a big part of this is understanding what we just found. What could you label that? What could you call what we just found there? Max error for both L10 and R10. That's the most that these two approximations are off. Are you with me? Let's just focus on L10 for a minute. So what that means is that L10, right? So that means the exact answer has to be somewhere between, and then what could I do with this max error? Couldn't I just add that on and take that off of this? Right? In other words, I could say that L is either, the most it can be off is 0.0642. So let's take 0.0642 and add it on to our L10. Because I know because we have R here, we know L is an under approximation, but let's pretend we didn't have that. Let's pretend all we had was L10. Okay? And we know it's off by this, but we don't know if it's under or over. So what's 0.26910 add this on? Point what? 3333. All right, and now take L10 and subtract that. 0.0642. What do we get? So what we know, this would be an error, this would be a bound on the integral. So what it's asking for, what your final answer is kind of depends what it's asking for. If they just want to know the max error based on the formula, we would stop right there, 0.0642. If they want a bound on what the exact answer is, well, we know that the exact answer is somewhere between there and there. Now, that's not very good. I mean, that didn't narrow it down to it very much, right? But what we can do is take the approximation we got, and we can add or subtract this because we know that's the most that could be off. Now, here's the other thing you want to think about. Remember we did Newton's method and we said however many zeros we have tells us our degree of, where our error is, right? So if I have 1 0, we might know we've got 1 decimal place of accuracy. Now we got to take into account rounding. So again, the 0.2, we'd say, well, we got 1 degree of accuracy. Now it's 0.26. So we do have, and you might say, well, that's a 6, so that could round to 0.1, whatever. You could say, well, I think we're within 1 decimal place anyway of the exact answer, right? Not very good accuracy, right? Not very good accuracy there at all, which we would expect, having only 10 of them. All right? So that's how that works. Now let's go ahead and do that with the midpoint one. And now the midpoint and trapezoid are exactly the same. The only difference is you got a 24 or a 12, right, in here. So let's go ahead and do our midpoint. All right? So let's do what is going to be our error bound for our M10. All right? So let's do our formula. Put our box here. This is going to be our K2 in here now. That's going to be K2. And then we have what? 1 minus 0. And then what did the formula say? Cubed. And then down here was, for midpoint, 24 times n squared. Right? So that's going to be 10 squared down there. Right? So that's just using the formula. We have 10 subdivisions again, so n is 10. Our a and our b, our integral is going from 0 to 1. And then we've got this K2 number. Now remember, so off to the side, I'm going to write down K2. I remember that K2 is the max of f double prime, absolute value. The max of the absolute value of f double prime. So let's find a number for that. Okay? So we need a number for K2. This is a fun one to come in the middle of, isn't it? Okay? I have a video. All right, so K2 is the max of the absolute value of F double prime. So we need F double prime. Now we already got F prime. So we can go up to there and grab it. And, oh, we should have probably done our derivative thing first, whatever. Okay? Or you can do second derivative. Remember, this one is second derivative right here, right? So you could just do it straight from that, either way. Or do the derivative of the derivative. So now we go derivative, arrow up and grab our derivative. There you go. So there's our second derivative. Now you can start seeing where copy and paste gets kind of nice. So I can arrow up and copy that. Go back to my graph screen. So now I want to graph the absolute value of that, right? Because we don't care about negative or positive, right? We just want the max. Yeah, you put it in F2. Now that'll mess up our zoom fit probably. So I would just go delete your F1. Just delete F1. Leave it in F2 is fine. Oh, and you forgot absolute value too. Yeah, so we can fix that. Okay. Just go in front of it and type ABS. Probably the fastest way to do it. Type ABS, left parenthesis. Now we'll put a, did it put a right parenthesis automatically? Oh, maybe it did. I wasn't sure it did. Oh yeah, it did. Cool. All right, go ahead and do that. So there's your absolute value. See how you can see how it bounced the negative part up. Now we need to do our zoom fit. We already have 0 to 1. We should already have 0 to 1 set in our settings. So if we just do a zoom fit. Okay, good. Now, where's our max? Looks to me like it's over at the right edge, doesn't it? So I would say let's trace. Yeah, I just type in a 1. I just type in a 1. I feel pretty good about it being there. Now, it did look like it was over here, maybe at 0. You might type in a 0 just for the heck of it. Yeah, that's 2. And if you go to the right here a little bit, just trace to the right. 2, 2, 2. See, it's not even changing enough. Now it's 1.99. So definitely at the right edge. So hit a 1 again. So definitely it looks like our max is at that right edge. Just type a 1.
Yeah.
Oh, it's still going. Okay, there's our K2 value right there. 2.28528. That's the max of F double prime, which is telling the curviest, right? The most concavity that this function ever has. 2.28528. 2.28528. So what would be a good place to round that one? 2.286 would be pretty good. You know, to be honest with you, I'd probably be fine with 2.9, 2.29, 2.3 might even be doable, but because it's 2.8, 2.9, it was 2.5, I don't think I'd round to 2.3. You know, I mean, but let's go 2.286. You're probably never going to get in trouble for going too far with these. The only thing you got to make sure you do is you round that up. Notice we had a 2 after. We still rounded that up to a 6, right? We want the worst case scenario. So we're going to always bump it up just a little bit at the end. All right, so let's put in 2.286. All right, and then we go ahead and we crank this out. 2.286, 1 cubed, we won't have to mess with that. And what's this, 2,400 down here? You can tell we're dividing by a much bigger number. No wonder there's so much less error, which we knew, of course, that midpoints and trapezoids had less error. What do we get? We 2.286 divided by 2,400. They give it to you as a scientific notation. So that'd be e to the negative 4. So that 10 to the negative 4 would be 1, 1, 2, 3. So it'd be 3 zeros. So 0, 0, 0. What was that? 9. 9 what? 952. 5. All right, that again is the max amount of error, which again tells us that we're accurate at least to 2 decimal places. We saw the example earlier where we had 1 0, but our digit wasn't right because of the rounding. So this tells you you're at least right in 2 decimal places. Now, if you go back to our actual answer, remember our midpoint was 309. Again, because of the rounding, you know, we knew this digit was right. This would round to 310, right? So if we round this and we round this, this would be 310, then this does tell us how many decimal places of accuracy we have. How many zeros here is how many digits of accuracy we would have if we were rounding. So we're starting to get a sense of how the calculator knows how many degrees of accuracy it has. Okay? Because we're calculating this max, this error here. Okay? All right, and if we subtract this, what is, Noah, just take this number minus that number. Go ahead and subtract that. It's giving us, these examples we've done, the max error is giving us a pretty reasonable approximation of the error, and partly that's because these functions are kind of, if you looked at K2, it was up there around 2 most of the time. Now it dipped down and came back up. So by us saying that this was the max and pretend that it had this the whole time, it pretty much was having that the whole time. Where you're off is when you get a function that doesn't have that nearly the whole time. What'd you get when you subtract it? 0.300448. Okay, so the amount of error we actually had was 0.0004 something. Our formula told us the most we could have been off is 0.0009 something, right? So that was the most error we could have. We know because the calculator did it for us, right? But we still haven't answered the question, how did the calculator do it? And that's the last problem I want to do for you right now, okay? So let's do it with a rectangle one. That'll be a little easier. So let's say we're going to take this same problem. We're going to take this same problem and we're going to ask this question. How many left rectangles will it take to be within 0.005 of the exact answer? This is what your calculator does to figure out how it's going to do the approximation. How many left rectangles will it take? Well, what that is asking really is, what does n have to be for my max error to be that? Does that make sense? What does n have to be for my max error to be that? Well, we simply take our formula, which would be K1, which of course is my box, and then it's going to be 1 minus 0 squared. Now we're talking about left rectangles now, right? So I'm using my left formula. I'm using this one. Okay? How many lefts do I need? And then what goes on the bottom here? 2n. So we're trying to find n. How many lefts do I need so that I get a max error of 0.005? Now, actually, I want the error to be that or less, right? I want that to be my max error, so the error could be less. So I probably should put a less than or equal to. So basically, I have to solve this equation. So we've got to find what to put in K1. Oh, gee, we already did that, right? We already did that. But if you were doing this problem, we'd have to figure out what to put in K1. So we'd have to do F prime, absolute value, find the max. Well, we did that right back here. We already got that number, right? We're doing the same integral, right? So we already got our max of F prime. So that's 1.284 is what we used there. So let's put 1.284 in, and let's solve this. Now, you can just let your calculator solve this. So we can just put this into a solve. Okay? The 1 squared is just 1, so you can leave that off. Okay? So it's 1.284 divided by 2n. Let's actually put a less than or equal to in there instead of an equal. Okay? Less than or equal to right in there. Let's put a less than or equal to 0.05, and then you have to have a comma n. Tell it you're solving for n. N can't be less than 0, so we can ignore that, right? So n has to be greater than 128.4. So what would we put for our answer? What was our answer? N is, what does n stand for? Number of subdivisions. So what are we going to put for our answer? Yeah, we're not going to put 128.4. We're not even going to write n is greater than or equal to 128.4. We're going to write 129. We need 129 rectangles to assure us that we will be within 0.005, and that's how your calculator is doing this. When you give it a problem like that, it is doing a quick calculation, really quick. You think about how fast it gives you those answers. It's figuring out, based on the information in the integral, it's taking this formula, because it's got the function, so it can do f prime, it can do that max. Okay, it's not really using lefts, but it's something similar to this. It's figuring out how many subdivisions it needs to guarantee we'll get that amount of accuracy. Okay, last thing I want you to do. I want you to go to the area program on your calculator now, and let's do 129 left rectangles. And let's see what it gives us. So we go back to the area program on our calculator. Let's put in 5 decimal places, put in our function again. I think you have to put it in every time. We're going 0 to 1. We're going to do 129 rectangles. Okay, let's do 130. Yeah, because it does them all for us, and it doesn't like Simpson's rule. Oh, did it give it to us then, though? Oh, it still did it. Oh, well, there it is. It's right here. Yeah, good. Okay, now, oops. Is that it? Yeah, that's it right there. Okay, now here's the left, 0.30701, right? Now, subtract that. That's 129 lefts. So 0.30701, and let's subtract what the exact answer was, which was 310, what was it? 310268. Subtract those two. This is our left. That's 129 lefts. Here was our exact out to that many decimal places, at least. What do you get? Okay? And we knew it, we said it was going to be within 0.005, right? And it is. Now, it looks like even less than that would have worked, right? 125 might have got us within 0.005. Or 120 would have got us within there. But that's not important. What's important is the guarantee. The formula guarantees that 129 left rectangles will get you within 0.05. It might get you even better, right? It got us within 0.03 something, okay? But it guarantees it'll get you within 0.005, and that's the secret. So it's really a pretty powerful thing. How it takes a number it doesn't know and guarantees that this number will be within a certain degree of accuracy of that. And it's all based on that worst case scenario that we did. It's all based on that K1 and that K2. And that's how a programmer is programming this calculator to do those approximations to give you those answers using that amount of information. Okay? All right. So your homework today is that next line in the homework, the third of the 4 lines on your homework sheet. And it's going to be stuff like what we just did. Basically, those are basically that's what the problems look like. Now, some of them won't be as involved in that. In other words, they'll just ask you parts of it, like they might just ask you for the K1 or the K2 value, right? So you just might have to graph the absolute value of F prime or graph the absolute value of F double prime, find that max, right? So use that zoom fit and all that stuff we were doing. Using it, but it's going to be a lot about these theorem 3 formulas, a lot about this kind of notation. You know, it might just ask you questions about, you know, I want you to understand this whole idea of worst case scenario and all that. On these approximations. So I can't find my assignment sheet. Oh, here it is. Okay. So if we look at the homework, number 1, it just, you know, it just basically has you go through that. Number 2, they just have you explain the concept of error bound. So this whole idea of what we were just talking about. 5 and 6, again, what is the, here's another way they ask a lot. 5, what does the theorem 3 say about the error? Okay, well, just do the formula. That's all we're saying. What does theorem 3 say about the error for T8? Do the formula. Right? I mean, what does theorem 3 say is every time they ask that, they're asking you to just crank out this formula, right? The right side of it. Number 6 says the same thing. They're pretty simplistic. You'll see when you get to number 7, but they're all just kind of different ways of working this out. Okay. All right, you get to use your, like I say, use your calculator for a lot of it.